polynomials. I am going to throw up some things, some terms that we had last week at one point, but I promise you it wouldn't be the only time you saw them. So when we're talking about a polynomial, the actual definition, if you look in a textbook, says like a to the n power, or sorry, a sub n x to the n power plus a sub n minus 1 x to the n minus 1. Okay, and this pattern continues through here. It's just telling us that a polynomial has a lot of different powers of x added together. The degree, we said before, is what? Highest power. In this scenario, it would be my n. What are the coefficients? What are coefficients in general? Number multiplied with the variables. Okay, it's all those a's up there. The constant is a term without a variable, which is that a sub 0. The key things that we are going to be using in this section, we need to know the degree, but the leading coefficient and leading term are going to have a big impact. The leading coefficient is the coefficient of the term with highest degree. The leading term is the term with the highest degree. And those are going to be the things that really dictate what our graphs look like. When we look at the degree, it's going to have a huge impact, and that leading coefficient is going to alter the shape of our graph. When we are talking about polynomials, the graph is always a nice, smooth curve. You don't have any corners, okay? It's just nice and curved, something like this. If we want to apply any transformations, it's the same rules we've already done, because x squared was a polynomial, x cubed is a polynomial. So those rules that we've learned in the past, they're still true. The other thing that we should add in, if we're talking about polynomials, all the exponents are whole numbers. So in a polynomial, you're not going to see a fraction or a decimal or negative in your exponent. All those exponents are 0, 1, 2, 3, 4, nice numbers. Is that okay? So first thing, I just want to look at some graphs or some equations, decide if they're a polynomial. If they are, we're going to give the degree. If they're not, we're going to tell why. So is the first one a polynomial? Yes. Degree, what's the highest power of x? Is b a polynomial? A square root is like what power? It's a 1/2. I said exponents have to be whole numbers. Is 1/2 a whole number? So it's that fraction exponent. In general, if it's a polynomial, you're not going to have a variable under a radical of any kind. What about c? Does that look like a polynomial? We said polynomials are just powers of x added together. What's wrong with this one? There's a variable in the denominator. Okay, so if we have a polynomial, we're not going to be dividing by a variable. So no variable on the bottom of a fraction, no variable under a radical. D, is this one a polynomial? Technically, yes. Degree, you have to think back. In section 3.3, the previous section, we talked about polynomials. And I told you degree is kind of like the number of variables with it. And I actually said this was a special case because 0 is the same as 0x. And isn't that the same as 0x squared and 0x cubed and 0x to the fourth and 0x to the fifth? Can you tell me what power that is? No. So I told you that's called a zero polynomial and it has no degree. It is the only such scenario, but because it's a zero, we can't specify what the degree had to be. Now E, is that one a polynomial? I mean, didn't break any rules, did it? Do I have fractions or negative exponents? No. It's a constant. It is a polynomial. The degree. Okay, 8 is not the same thing as 8x, is it? What's the power on the x have to be? 0. So the degree here is 0. Because in general, a constant has no variables with it. Degree is kind of like how many variables do you have. F. This one is factored. But if I multiplied it all out, would it look like our definition of a polynomial? Yeah. So this one is, and we are going to see a lot of polynomials written like this. Our degree. We have to think about it a little bit. Degree is the highest power when all the terms are added together. So if we really wanted to, we can multiply this all out. It wouldn't take us too long. Or we can think about it. If I multiply this out, what would my highest power of x be? So if I think right here, I have 3 x's. And here, I would get an x to the second. So I have 3 here and 2 here. So when I multiply them together, we would have 5. Because when you're multiplying, you add those exponents. X cubed times x to the second would equal x to the fifth. So that's kind of a trick we are going to be using today as well, to identify the degree when things are in factored form like that. All right. Any questions so far? So here is what I want you to do. I want you to take a couple minutes. I don't care if you want to turn and talk to someone next to you, and draw me a rough sketch of all 4 of these things. So a few exact points. Get me that a sketch. What do you think about A and B? Okay. Yeah, A was our x cubed that we've seen before, our chair. And if you only put in 0, 1, and -1, x to the fifth looks much the same because those 3 points turn out to be the same. The difference would come when you put in 2. 2 to the third is 8, but 2 to the fifth is 32. So this one, it's the same shape, but it's a little bit steeper. It's getting bigger faster. What's x squared look like? Parabola. What's x to the fourth look like? Yeah. So again, we have the same points if we put in 0, 1, and -1. But if we put in like a 2, 2 squared is only 4, whereas 2 to the fourth is 16. So it's steeper. So what do you think dictates what these graphs look like? A and B look the same. Why? The powers were odd. C and D look the same, and their powers were even. Okay, so if you just have x to a power, it will resemble x squared if that power is even, and x cubed if that power is odd. So it'll look generally like a parabola or a cube. As the power becomes larger, what happens to the graph? Yeah, it's getting taller and skinnier, right? I'm just going to put the graph in arrows. Okay, we just keep getting skinnier looking parabolas. If I did x to the 6th, it would be even skinnier. X to the 8th, even skinnier. This idea is actually what's called end behavior. And it will allow us to look at a polynomial and have a general idea of what its graph will look like without ever picking up a graphing calculator or plugging in any points. So, end behavior is what happens as x becomes large in the positive or negative direction. It is determined solely by the leading term. Okay, so that's the term with the highest power of x. If that leading term has an even degree, then what did we just say it was going to look like? A parabola. Okay, so if the coefficient is positive, it's a regular parabola. What would happen if that coefficient were a negative? If I said negative x squared, it flips it and it becomes an upside down parabola. So if you have to look at the whole term, the degree tells me it's like a parabola, but the coefficient tells me if that parabola is opening up or down. Just like we had in our last quiz. I gave you a question and said, okay, does this parabola open up or down? It's based on if it's a positive or a negative. If your leading term has an odd degree, then if our coefficient is positive, it's going to look generally like an x cubed. So the left end is going down, the right end is going up. What do you think would happen if I put a negative in front? Now, in terms of end behavior, you can draw yourself a picture. You know, if you want to write like this, you can. If you look in your textbook, it does not use the same type of notation. I'm drawing 2 arrows. Your book is going to say, as x approaches negative infinity, f of x approaches infinity. And as x approaches positive infinity, f of x approaches positive infinity. Okay, and that's just another way of saying it is x goes forever in the negative direction, the y is going up. As it goes forever in the positive direction, the y is going up. You can write that if you really feel like it, but we might as well just draw 2 arrows. That's going to be a better visual for us when we get ready to draw our graphs anyway. So I'm just going to draw my arrows. All right, any questions about that? Okay, so I want to look at some and just identify end behavior. The only thing I look at is the leading term. Now, is the leading term necessarily the first term? Doesn't have to be. I find the one with the highest power of x, which does happen to be first. When I see x cubed, I'm thinking, okay, it looks like a chair. Does the 4 flip it?
Nope.
Nope, it's positive, so it's my normal chair. So the left end is going down, the right end is going up. The second one, all I'm looking at is my negative x to the 6. So the 6, even power, what does that tell me? Both ends are going up. The negative coefficient tells me flips them straight down. The next 2, we have to do a little more work. These are written in factored form. In order to decide the end behavior, we need it to be multiplied out, okay? But I don't really need the whole thing multiplied out. All I care about is that first term, right? So I'm going to go through, I'm totally cheating, okay? I'm not doing all the math here, but we have a 3, okay? If I take the highest power of x, that would just be an x. This parenthesis would give me an x to the 2nd. So when I multiply this all out, my leading term would be 3x cubed. Do you guys understand where I got that? X cubed tells me what? Like a chair. Yep, ends are going opposite directions. Does the 3 flip it? No. Positive coefficient stays the same. So the left is going down, the right is going up. All right, this one. All we care about is that first term. So if I were going to multiply this out, all I care about is my highest power vector from each parentheses. So the first parenthesis would have an x squared. This one, if you have x squared to the third, what do you do when you have a power to a power? So that would give me a 6. The last parenthesis, x to the 4. So now when I'm multiplying all these x's, what do we do with our exponents? Add them. So 2 plus 6 plus 4 is 12. So the highest degree is going to be 12. I have a positive 1/2 in front. An even degree tells me what? Both ends are going up. It's a positive 1/2, so does it flip? No. So end behavior is up, up. All right. That is the first third of your homework tonight. Just drawing 2 arrows, telling me what end behavior is. Are we okay with that? All right. I want to get through a couple more things before we end today. If I ask you to create a polynomial, what does degree tell me? Highest power. Okay. This we should know from our last section. If -3 is a 0, what's in my polynomial? If 2 is a 0. If 5 is a 0. Okay, does this have degree 3? If I multiply it out, x times x times x is x cubed. So that one meets all the requirements. We don't have to do anything else. Okay, B. Let's start with the zeros. If 0 is a 0, what do we have to have? X. If 4 is a 0. If 12 is a 0. Okay. What's the degree of this currently? 3. How could I make it a degree 4? Yes. Does it matter which one I square? Nope. I didn't tell you. So any one of them you could add a square. And now it's degree 4. Okay, C. If -1 is a 0, we have? If 1 is a 0. If 2 is a 0. Okay. Is that degree 3? One more thing. We had some problems like this when we were dealing with quadratics. If I give you the y-intercept, what does that mean? Okay, if it were all multiplied out, my constant term would have to be 1, right? When we were talking about it with quadratics, we said, well, there could be a number in front, right? And didn't we find that a value? What did we do to find that a? What did we plug? 0. So if my x is for 0, I know this thing has to equal 1. So 1 times -1 times -2, so we get a 2a equals 1. So a had to be 1/2. So I have to have 1/2 times x plus 1, x minus 1, x minus 2. Trying to pull in some of the different things that we've been talking about with our quadratics and our polynomials here. Any questions there? The next piece is just some terminology. So if I ask, a 0 is just a number, right, that makes the function equal 0. So if I say, give me a 0, you're just saying 5 or 3 or whatever. Another way to say the same thing is saying x equals c is a solution to p of x equals 0. When x is equal to that number, my y is equal to 0. Factors have the x with it. So a 0 is just a number. A factor is x minus that. That's the big thing we did in the previous section. You had to write your factored form when you had all the x's, and you had to list your zeros, which is just the numbers. In terms of a graph, a 0 is an x-intercept, okay, because it's a place when y is equal to 0. So it's where it hits the x axis. So that we are going to be using a lot tomorrow when we actually start graphing this. All right, last couple things. If I give you a factored form, can you tell me the zeros? Okay, if I look at this, does 5 ever equal 0? What would make x minus 2 equal 0? What makes x plus 3 0? And why do we have a multiplicity of 2? The square. Multiplicities are going to change our graph, so we need those. What makes x minus 1/2 equal 0? 1/2 multiplicity would be 4. You guys do B. Tell me the zeros and multiplicities for each. So if you just have a plain x, what's your 0? Okay, x plus 1, 3x minus 2. If you need to, go off to the side and work it out. You need to know when that equals 0, so you get good. And x minus 5. Okay. So I want to mention what this is going to do to the graphs. I've been telling you multiplicities are important. Here's what happens. Okay, if you think about like x squared, what's the only 0 of that? 0 with a multiplicity of 2. When you graph a parabola, what happens at 0? It touches and bounces off, right? If you think about x cubed, what's my 0? Just 0 with a multiplicity of 3. When you look at that graph, what happens at 0? Crosses and goes through. So, in general, if your multiplicity is odd, then our graph is going to cross or go through at that point. Okay, whatever that point might be, let's say this is my x-intercept. So, the graph goes through that point. If your multiplicity is even, at whatever it might be, your graph will bounce. So, odd multiplicities, the graph is just going to go through the point. Even multiplicities will bounce. Final thing I'm just mentioning today, and I'm done after that, a turning point on the graph is just anywhere where the graph changes direction. But it is very closely related to the degree of the polynomial. So we're going to touch on this, and then that's my stopping point. So if you have degree n, you have at most n minus 1 turning points. Okay, what do you think I mean by a turning point? Changes direction, okay? So if I said a degree 3, it would be possible to have a degree 3 like this. Okay, it hits the x-axis 3 times. It has 3 zeros, so degree of 3. How many times did this change direction? Twice. So your degree, you can have at most 1 less than that for your turning points. Now, I say at most, because if you think about your standard x cubed, does it have any turning points? No. But if I look at this, I see 2 turning points, so it has to be at least degree 3. It works in reverse. If you know your number of turning points, your degree has to be at least 1 bigger. If I drew this graph, how many turning points do I have? 4 turning points. So my degree has to be 5 or more. And the final thing I'm not even going to touch on right now because we're going to hit it tomorrow. So, any questions for me? There is a handout posted on Math Excel. It should be a pretty short one. The first 8 questions just ask you for end behavior. So I'm asking you, draw me arrows, okay? The next 4 questions say how many turning points. So if my degree is 7, how many turning points can it have? 6. If my degree is 12, I can have 11 turning points. And then the last ones have some graphs and you answer some questions about those. So you guys have time to work and ask questions right now.